Welcome back. Now it's time to talk about why you have been measuring the altitude of the sun at noon each day and to explain why that number is changing from day to day. You should be familiar with the notion of the celestial sphere. I've drawn it here. One way of thinking about the structure of the universe is that Earth is at the very center, or you're at the very center, some of you, and there's an enormous fictional sphere around us that's called the celestial sphere. And just like the line around the midsection of the Earth is called the equator, there's an imaginary circle. It's called a great circle because it's the greatest possible circle you can draw on the sphere, meaning circle with the greatest possible radius. That's the celestial equator, and we've got poles as well. So we know that the Earth rotates about its own axis. If you extend Earth's axis of rotation and look at the 2 points where that axis intercepts the celestial sphere, we call those the North Celestial Pole and South Celestial Pole. And remember, there's a very special star named Polaris, which happens to be very close to that axis. It's not right along the axis, but it's close enough that you've been using that star to determine the direction north in your lab. So let's consider Shakira here standing at the North Pole of our planet, gazing at the constellation Orion. So we'll take this to be sometime in the winter. And let's actually move to Stellarium to better visualize the celestial sphere. Here we are, back in our favorite piece of software. Let's do a couple things. For one, let's turn off the atmosphere so that the air no longer scatters the sun's light. If we didn't have an atmosphere, you might look up into a dark sky and see the sun during the daytime. No sky. And I would like to change the projection scheme here. So it's not easy to take three-dimensional space and plop it into a two-dimensional space like the screen of your computer. There's multiple ways of doing that. They're called projections, and you can actually change which projection is being used in the options here. So if you go to Sky and Viewing Options, down here in the lower left, you can take your pick of projections. The stereographic is a very commonly used, popular projection, but let's try out the orthographic projection. And this one's kind of neat. It's like they've taken three-dimensional space and wrapped it around this sphere and stuck it on your two-dimensional computer screen. And this is not quite how I ideally would represent the celestial sphere, because you'll notice that the ground of the Earth is also there, but the celestial sphere is not supposed to be including Earth. It's a dome really far from the Earth. If I tap the letter Q, I can get rid of the cardinal directions. And let's speed up time here and watch how things rise from the east, make their way across the sky, and set over in the west. So this is a nice way to visualize the celestial sphere. If I tap the letter E, I can put a coordinate system up on that sphere, which is very reminiscent of latitude and longitude. What's going on here? Latitude and longitude on planet Earth. It's not quite the same thing. Okay, so the idea is every object you can see in the night sky, stars, the sun, the planets, you can think of them almost as if they're painted on this massive dome with an extremely large radius, much larger than the radius of the Earth. So that dome is really far away, and most of the objects, the stars in particular, stay basically in one place on that sphere. Yes, the whole sphere is turning. Hang on a second. Yeah, the whole sphere is turning around us once a day, but the stars stay fixed in their relative positions. The planets, on the other hand, will visibly wander, and my program is getting stuck here. Back to Shakira here. So this particular star in the constellation Orion is called Betelgeuse. Many of you are familiar with it. And I've drawn the line of sight from Shakira's eye to that star. So this line or ray indicates the direction that she would have to look in order to see that star. Now, in this picture, it seems as if she were to go down to the equator, she would have to look in a different direction. Do you see how this ray is not parallel to this ray? And that effect is called parallax. When you're looking at something fairly close to the Earth, the direction that you would have to look will change depending on your location on Earth. So somebody at the North Pole would be looking in a different direction than somebody at the equator. It's just like when you're in a car on the freeway. Let's say you're looking at a building next to the side of the freeway. Your head is pointed in a particular direction. As your car moves, another 500 feet down the freeway, you have to tilt your head in a different direction to continue looking at the building. And that's actually a misleading suggestion from this diagram. So let's, instead of having the camera view slightly above the Earth, let's look at it directly from the side here now. So here's the celestial equator. We're looking right through the sphere. And a better way to think about it would be to make the celestial sphere larger in radius. Remember, the radius of that celestial sphere is way greater than the radius of the Earth. You might even think of it as being practically infinite. So this is a better representation than this. And notice what happened to these two rays as I went from this silly picture to this slightly less silly picture. These two rays are now more nearly parallel. The two directions that Shakir would have to look to see that star, Betelgeuse, from the top versus the equator, or the North Pole versus the equator, those two rays are more nearly parallel. Here they're very clearly different. And if we continue that even further, and so I've practically run out of space on the screen here, so instead of making the celestial sphere bigger, how about we make planet Earth smaller? And even smaller still? Do I have another? No. Okay, that's as small as I went. And you can see that these two rays are becoming even more parallel. So something really important to keep in mind here is that this notion of the celestial sphere only works if you regard the sphere as being of infinite radius. It's got to be really far away. And if you took this sphere super far away, you would see that these two rays really would become parallel. So for an object super far away, like a distant star that's 20 light years away, the direction you look to see it from the North Pole and the equator are essentially the same. Yes, there's a very small difference, but it would be very difficult to measure. Just treat those lines as parallel. So it doesn't matter where you are on the Earth, there's one direction that you look to see an object on the celestial sphere. Okay, so now the object in question I've placed at the celestial equator. Instead of Betelgeuse up here, let's imagine that the particular star we're looking at is on the celestial equator. And so Shakir would have to look, when she's on the equator, she'd have to look straight up over her head to see that star. And the idea is, if she then went to the North Pole, no, she would no longer be looking over her head because her body is oriented differently, but the line of sight to see that thing would now be parallel. So don't be misled by what you see here. The picture suggests that in order to see this star, Shakira, while at the North Pole, would have to look off in this direction. But that's only because I couldn't actually draw a celestial sphere of infinite radius. So if she's looking in this direction, she will see that star because the idea is it's really far away and these two rays would become parallel. So I will always use the direction from the equator to be the actual direction in which you would look to see an object on the celestial sphere. Now let's go back to supposing that the object we're looking at is above the celestial equator. And there's an important angle that we need in order to do this lab. It's a lot like latitude on planet Earth. So for a moment, forget about planet Earth here in the center. Imagine that this circle represents planet Earth and that this was the equator of the Earth. We know that this angle measured from the equator, we've got two rays that meet at the center of the Earth. That angle is called the latitude of a person living on planet Earth. And we live in Long Beach at about 33 or 34 degrees north latitude. On the celestial sphere, it's not called latitude. There's a special name. It's called declination. Where's that slide? Here we go. Declination. And we use this very often, this Greek letter delta. This is lowercase delta for declination. So I'll be doing that in these slides here. Try to remember it's like latitude on planet Earth. Different name. And I'm just estimating that particular angle in this slide looks to be a little less than 45. And now let's examine declination in Stellarium. Now, if you hear my voice cut out or get choppy or speed up and sound silly, it's because, I don't know, maybe I'm low on RAM in the computer, but sometimes it gets kind of stuck here. Okay, what's the first thing I'd like to do here? Let's turn off the atmosphere again. I'm going to zoom out a bit. And let me tap the letter Z again. Remember, we've got this local coordinate system, the altitude, azimuth coordinate system, which corresponds to the way your head works. When you turn your head left to right, you're scanning along lines of constant altitude. And when you tilt your head up and down, you're scanning along lines of constant azimuth. So that's a very natural coordinate system. But because we live not at the equator and we're standing on this sphere, the coordinate system that's most natural for our head is not the same as this coordinate system for the celestial sphere. I just mentioned declination. So let me turn this off and tap the letter E now. Some of this hopefully is review. If we look at the North Pole and speed up time, we can see all the circumpolar stars rotating around the North Celestial Pole. This is the North Celestial Pole. Okay, this is a bummer, but I think I had to close all my other applications so that my computer can handle this. Okay. Those are the stars making circles around the North Celestial Pole, and that's why this coordinate system is more natural. You see these blue lines are not the same as lines of constant altitude and azimuth. Let me get rid of the ground now. And you see how everything looks kind of tilted? I can go down here and change the way the telescope is mounted, and this is now an equatorial mount. So right now I'm scanning along the celestial equator. You can see it says 0 degrees here. That's 0 degrees declination. If I turn off the coordinate system and hit, what was it? There we go. If I hit the period button on the keyboard, I'm looking at the celestial equator. There's also an option to display the poles, but if you put the equatorial coordinate system up by tapping E, that's included. There's the NCP, there's the SCP, South Celestial Pole. And if I just pick something arbitrary like the moon, we can see that the moon is above the celestial equator. So it has a positive declination. I can zoom in here. Here's the celestial equator. Everything on this line is 5 degrees above, so that's a declination of 5. Everything on this line has a declination of 10. It looks like the moon is at around 22 degrees declination. And we can confirm that by going over here, and you'll be doing this in the lab for the sun. RA/dec, that's right ascension, which is a lot like longitude on the celestial sphere, and dec, which is declination. Notice there's two rows that say RA/dec. Go with the one that says on date. So Stellarium is telling us that on November 3rd here at around 12:57, the declination of the moon is about 21 degrees and 50 minutes. And now actually is a good time to show you how to display those angles in decimal form rather than degrees, minutes, seconds. So let's fix that right now. Is that under configuration window? It might be. Tools. Here it is, use decimal degrees. So again, you go into configuration window, the tools tab, and check use decimal degrees. And it's already updated. Great, this will be more convenient to work with. So this is where you will look to get the declination of some object that you've clicked on. Let's check the declination for something below the equator. How about Rigel, one of the stars of the constellation Orion? It's below the equator, so I expect it to have a negative declination. There it is, negative 9.2. And you'll notice it actually is changing. That's kind of wild because I mentioned, let me tap the letter K to stop time. I mentioned that the stars stay fixed on the celestial sphere, whereas the moon wanders around. I mean, if we click on the moon and I unpause time, hang on a second. Now I'm surprised. Okay, the declination is changing but it's rather slow. If I tap on Rigel again, okay, good. So I do not see that number changing. I must have been looking at another number, but you'll notice that these values are very stable. Don't forget that even the stars are actually flying through space, so given enough time, their positions on the celestial sphere will noticeably change. What happens if I go up to the, nope, that's the location window. Let's go to the time window, and I'm going to skip ahead like 1,000 years. So look at this value, 8.1783. What happens if I change this to the year 3020? Aha, that number definitely changed. But over a period of days, months, you're not going to see it change much. Okay, we're interested in the sun. So let me click on the sun now. The sun currently has, am I back in the year 3000? 2030, let's fix that. 2020. It's been an interesting year thus far, and we're not even done. Okay, the sun currently has a negative declination. Remember, it's kind of low in the sky right now at the beginning of November here. So I'm going to speed up time, and you'll notice that the sun is moving along the celestial sphere. In fact, it's moving along that special line that we call the ecliptic. And it takes a whole year for the sun to transit the ecliptic. Let's throw up some constellations here with their labels. So the sun's moving through Gemini, now Cancer, then Leo, and you see why those constellations are familiar to us, at least their names, because those are the constellations that the sun passes through. So it's obvious that the sun's declination is changing. Right now the declination is negative because the sun is below the equator, but in spring, sometime in March, the declination will go positive again. That's called the spring equinox. So the fact that the sun's declination is always changing, that's why you have been observing this change in the sun's altitude every day at noon. So here's Shakira again, standing on top of the world. And if we were interested in seeing a star down here in the southern hemisphere of the celestial sphere, we'd have to look off in this direction, and that declination would be negative, we just saw. And remember, if we're talking about a star, stars are really far away. Yes, the sun is also far away, but its declination does change. The stars are so far away that it doesn't matter whether you're at the center of the Earth or at the equator or at the North Pole. The direction you have to look is fixed. That depends on where the star is on the celestial sphere. So that parallax effect is negligible. Keep that in mind as we go through these slides. So remember, if you're standing on Earth's equator, you would go straight up from the Earth, off in that direction to see the celestial equator on the celestial sphere. The celestial equator is really the projection of Earth's equator onto the celestial sphere. So this gal at the top of Earth, she would have to look in the same direction. So don't think of the celestial equator as some nearby point right here, so that she would have to look kind of down to see it. No, it's so far away, the direction is the same no matter where you are on Earth. If she's looking at an object on the celestial sphere, like a star, that has a positive declination, meaning way out here on the sphere, it's above the equator, then she would have to look in a direction above the forward direction, because this is the direction to the celestial equator. Anything north of that would be above. And if she's looking at anything below the celestial equator, meaning anything with a negative declination, she would have to cast her gaze downwards. Now, because sometimes the declination is negative, if I want to talk about just the magnitude of this angle, like how big it is, I would refer to the absolute value of the declination. Like the number -3, for instance. Its absolute value is just 3. Now that's not real important to this discussion, but okay. Now what's her latitude? Hopefully you know that somebody living at the North Pole, like Santa Claus, has a latitude of 90 degrees. That's the angle measured from the equator. Here she is living at a lower latitude. Maybe this is something like 45 degrees. So latitude is measured from the center of the Earth. There are two rays from the center of the Earth to her and the center of the Earth to the equator. The angle between those two rays is what we call the latitude. And let's use the letter phi for the observer's latitude. And now we have to talk about altitude. So this is going to get a little tricky, but we have to go through this in order for you to understand what's going on with the change in the sun's altitude from day to day, which hopefully you've been measuring. Okay, so remember, this is the direction to the celestial sphere. It doesn't matter where you are on Earth, that direction's the same. So for her, this ray leaving her eye is going towards the celestial sphere. And because she's looking at an object with a negative declination, she would have to look off in this direction to see that object. So whether it's a star or a quasar or whatever, this is the ray to the object she's interested in looking at. Now, remember, the horizon is the direction to the horizon is parallel to the ground. See how this is the tangent line to the ground? This would be the flat surface that she's standing on. And for her, the horizon would be the direction parallel to the ground. And what do we call the angle between the direction to an object in the sky and the horizon? Well, now we're back to altitude azimuth. That's what we call altitude. Altitude is the angle between the line of sight to an object you're looking at and the horizon, which is straight out in front of you. So I'd like to find a relationship between latitude of a person, the declination of an object on the celestial sphere, and the altitude of that angle as seen by somebody. And I should point out now that we're looking at a two-dimensional picture here. It's more difficult to visualize in 3 dimensions. So this picture really only works if you're talking about an object that is currently on your local meridian, like the star Fomalhaut that you've been looking at. When an object is crossing your meridian that's due south, then this picture is applicable. If it's anywhere else, it's more complicated. So now we have to introduce one more angle here. I mentioned that we're 34 degrees above the equator. Well, this whole thing is 90 degrees, right? Equator to the direction to the North Pole. So what's 90 minus 34? Well, 90 minus 30 is 60, so 56. If this was 34 degrees latitude, this other angle would be 56 degrees, and that's called the colatitude. Colatitude is basically how many degrees you'd have to walk down from the North Pole to get to where you are. So if you live in Long Beach, you'd have to walk 54 degrees down from the North Pole. That's your colatitude, and that ends up being a useful angle here. So let's call that theta. Let's introduce another number or another symbol for that angle here. So what is the relationship? And right here I'm reminding you, colatitude is 90 degrees minus latitude. They're complementary angles. They both add up to 90, or together they add up to 90. Okay, so let's look at the relationship between the colatitude theta, which is this big red angle, and I skipped that part. Yes, it's not at all obvious that this angle is the same as this angle, but let me emphasize this. However many degrees you have to walk down from the North Pole to get to where you live, that's called the colatitude. That's the same as the angle between your horizon and the direction to the celestial sphere, to the celestial equator. Remember, this line goes out to the celestial equator, and this ray here is parallel to that ray. So once again, your colatitude, wherever you live, is the same as the angle from the horizon up to the celestial equator. And I've got some more slides that should help convince you that that's true. But let's look at the relationship between theta, altitude, and declination. Really the absolute value of the declination. Maybe you can see it right here in the picture. This angle together with this angle is this total red angle. You just add them up. So evidently from this diagram, colatitude is the same as the altitude of the object you're looking at plus the absolute value of its declination. Remember, we looked at stuff that had a declination of like -9 degrees. This would be the +9, absolute value. Well, remember from high school math and before, let's say you're adding 5 to the absolute value of -3. Well, that's the same as adding the negative of -3. Negative negative is positive. This would just be 8. How do you get the absolute value of a negative number? You take the negative of that number, right? The negative of -3 is +3. That's how you get the absolute value of a negative number. So let's do the same thing over here. Remember, she's looking at something below the celestial equator, which means it would have a negative declination. So if this number is negative, we take its absolute value by taking the negative of it. Okay? So if delta is already a negative number, negative would give us a positive number. Of course, a plus negative delta can just be written a minus delta, right? 5 plus -3 would be 5 minus 3. That's a different example there than the one I had in the slide previously. Okay, so this is the overall equation we're interested in. Your colatitude would just be the altitude of something minus its declination on the celestial sphere. Let's solve this for A, because remember, you've been measuring the altitude of the sun at noon with a clinometer. You did that experimentally. And now we've got a relationship between these three quantities. So add delta to the other side, and you get this equation. I've solved for altitude. The altitude of anything in the sky should be your local colatitude plus the declination of that object. And what's cool about that is if you're in one place, like if you're not traveling, just look up your latitude and this number doesn't change. Your colatitude doesn't change. If you're going to stay in Long Beach for the next few weeks, your colatitude is basically 56 degrees. You can look that up more precisely on Google Maps. So then you can go into Stellarium or some other star database, get the declination of any object, add that declination to your colatitude, and that will tell you where to look in the sky, how high in the sky to look for something when it's culminating, meaning when it's crossing your meridian. Because remember, this picture only works for something that's due south. So this woman here, she's actually facing south. So if we continue on in this direction, we would reach the South Pole. So just to review of the terms, A is for altitude. That's the altitude seen by this particular observer, and that does change depending on where you are. If you go to a different latitude on planet Earth, that altitude would change. Of course, so would the colatitude. If you go to a different latitude, obviously your colatitude changes as well. Colatitude tells you how close you are to the North Pole. If your colatitude is 1 degree, you've only walked 1 degree down from the North Pole. Your latitude would be 89 degrees. This is the one that basically doesn't change for stars. It takes a long time for the declination of a star to change because they're so far away. The sun, on the other hand, is moving up, and it's moving above and then below the equator every year, the celestial equator. And so its declination is constantly changing. Okay, these slides should help you visualize how the altitude of something should change as you move down the Earth. Now, this is a little contrived because to get from, especially if you're walking, to get from the North Pole to the equator, I'm assuming would take years, at the least months, especially, how are you going to go across the ocean? But supposing you could zip from the North Pole down to the equator in a matter of minutes or hours. You can imagine first standing at the North Pole, and I didn't draw a person here to keep the diagram simpler. So let's pretend that this arrow is like the body of the person. And they're currently at the North Pole. That's what's indicated by this white bar here. So their latitude is 90. Now what would their colatitude be? 90 minus 90 is 0. So when you're at the North Pole, your colatitude is 0. And if you're looking at something off in this direction, see how this ray is parallel to this ray? And let's just pick the sun as our object here. Now, it's true, the sun is nowhere near as far away as the stars. So if you move from the equator to the North Pole, there would be a little parallax, like you'd have to tilt your head a little bit, but it's a very small effect. Let's just forget about it. So if you're at the center of the Earth and you'd have to look in this direction, to see the sun, then the same thing will be true at the North Pole. That's why this ray and this ray are parallel. And you'll notice that this angle is the angle between the horizon. Remember, the horizon is always tangent to the Earth where you're standing. It's the angle between the horizon and the direction to the star. That's what we call altitude. Now, in this case, the altitude, or that angle, is below the horizon, so you wouldn't actually see the thing. You know, it's below the horizon. You can only see things that are above the horizon. But imagine now that you're going to walk a little ways towards the South Pole. So face south and start walking. Eventually you get to here. So this represents your body vertically from the Earth. And notice that your latitude has now decreased a little bit. It's a little less than 90 now. So your co-latitude is probably a few degrees. And look what happened to the altitude here. It's still negative. The object you're looking at is still below the horizon. So you wouldn't be able to see the sun here. But that angle got smaller. We started here. Now it's smaller. If we continue like this, altitude continues to get smaller. See how I'm now farther from the North Pole? Eventually, you're going to get to a point where this altitude closes up to 0, and then the sun would be at the horizon, like it's just coming up. Again, this is a little difficult to picture in this diagram because nothing is to scale here. The sun is very far away. The Earth is super tiny compared to the sun. But if you're standing here, to see the sun, you would look in a direction parallel to the direction you would look if you were at the center of the Earth. That's the whole idea, is that the sun is so far away that these rays are parallel. Okay, now, you've gotten far enough down from the North Pole that this object has now popped up above the horizon. So I've drawn the horizon line. See how it's still tangent to the Earth? And you still would have to look in this direction to see the sun, because that's the same direction as this ray down here. But now, the direction to the sun is actually above the horizon. So you can now see the sun. And if I had to guess, this looks like, what, 30 degrees, 35 degrees. If you continue to walk south, down towards the equator, now watch what happens. Now the horizon points off in this direction. Again, this is your body, so this would be the zenith. I didn't want to clutter the diagram, but this direction is to your zenith, the point right over your head. You still have to look the same direction to see the sun, but now the angle between that direction and the horizon has gotten bigger. See that? Let's watch these two slides here. This is the sun getting higher in the sky, even higher, but notice how this ray doesn't change. I'm going to go through those two slides again. Watch how the direction to the sun does not change. I'm scooting the ray around so that it starts on the surface where the person is standing, but this direction is not changing from one slide to the next. So I'm hoping that you're imagining yourself starting at the North Pole, walking south, and as you continue to walk, you can see the sun getting higher and higher in your field of view. And it's not because of the rotation of the Earth, because I'm imagining that we're doing this in a matter of minutes. Remember, it takes a whole day for the sun to go around us. So just imagine you're moving so quickly over the surface of the Earth towards the equator, due south, that you can actually see the sun change locations. And now let's use Stellarium to try and imagine that better. Here we are back in Stellarium, and I hit the semicolon button to put up the meridian, and I adjusted the time until the sun was just crossing the meridian. So the sun is culminating, and I'm somewhere north of Los Angeles here. So let's now put ourselves at the North Pole. I can go to the location window, and let's see here. I just want to put my latitude up close to 90 degrees. So let me change this to, instead of 34, let's go with 89. If I've noticed that if I put it all the way to 90, weird stuff happens. So for now, I'll just go with 89 and some change. And I don't see that updating for some reason. There we go. Now what happened? Well, right now the sun is below the celestial equator. So if you're at Earth's North Pole, it would be below, the sun would be below the horizon. And that's why it's dark here. Maybe it's because did I turn off the atmosphere? Okay, so you can sort of see the glow of the sun down there. If I get rid of the ground, aha, there's the sun. Now what I want to do is pull up the location window and imagine myself walking down towards the equator. So I don't see a red arrow here. I started off north of Los Angeles, so we were somewhere here, and then I increased my latitude almost to 90. So I'm right about here. Watch what happens if I click a little farther south. Aha, so imagine we've just walked, and again, this is silly because the background picture here of the ground is not updating, but imagine you've now walked, a couple hundred miles, several hundred miles due south towards the equator. You would see that the sun appeared higher. I'm going to continue that, so another couple hundred miles. I just keep going. And maybe you've even frozen time, or the Earth is not rotating. Forget about the effect of the Earth's rotation. So you've frozen the Earth's rotation. You're seeing the sun rise higher simply because you're walking down from the North Pole towards the equator. And so the sun's altitude gets higher and higher. So the altitude of the sun has something to do with your altitude. With your co-latitude, right? At the North Pole, your co-latitude is 0. At the equator, your co-latitude is 90. So as your co-latitude increases, as you're walking down from the top of the Earth, the sun will appear to rise higher and higher in the sky. In other words, its altitude will increase. And if I keep on going, it just gets even higher. Okay. So let's repeat the previous slides now in PowerPoint, but this time with some more detail. So if you're standing at the North Pole, again, your latitude is 90 degrees, but your co-latitude is 0. And suppose we're looking at the sun while it's in the southern hemisphere of the celestial sphere, so it's got a negative declination. If you were at the center, let's suppose you'd have to look in this direction to see the sun. That means same thing applies at the North Pole. You'd have to look down in this direction. Well, that would be below the horizon. We know that we cannot see something below the horizon. And then imagine walking a little ways towards the Earth's equator. So now we're down here. I've indicated the co-latitude in red here. And do you see how maybe these two slides will help you visualize why this angle is also the co-latitude. This is the angle between your horizon and the direction to the celestial equator. So right now, your horizon is the same as the celestial equator. Do you see that? If you're standing at the North Pole, when you look straight out ahead at the horizon, you are looking at the celestial equator. You can check that in Stellarium. So if you now walk down towards the Earth's equator by, let's say, 2 degrees, your horizon will also dip down by 2 degrees. And now there would be a 2-degree angle between your horizon and the direction to the celestial equator. So I think that makes it pretty clear. Your co-latitude is the same as the angle between your horizon or the direction to your horizon and the direction to the celestial equator. Okay, so this is the co-latitude theta. And remember, altitude, just stick one finger towards the thing you're looking at, stick the other finger, hold your arm out towards the horizon. Altitude is the angle between those two directions. So in this slide, the sun is still below the horizon, but the absolute value of the altitude got smaller. See how this altitude, the angle between horizon and direction to the sun, is smaller than it was previously? And the declination has not changed at all. The declination is still the direction between, it's still the angle between the direction to the celestial equator and the direction to the thing that you're looking at, in this case, the sun. If we go even further towards Earth's equator, keep walking south, eventually you will get to a point where your horizon points in the same direction as the thing you're looking at, in this case, the sun. And if that's true, then the altitude would have to be 0. Does that make sense in this diagram? If you look straight out at the horizon, you're actually looking in the same direction as the sun. In other words, the sun is on the horizon. And that happens when the co-latitude, you'll notice, is the same as the absolute value of the declination. Remember, this angle between the ray to the celestial equator and the ray to the sun, that is the sun's declination, or it's the absolute value of the sun's declination. I say absolute value because it's a negative number here. And in this diagram, you can see that's the same as the co-latitude. Okay, so when your co-latitude equals absolute value of the declination, then the object you're looking at is on the horizon. Now we've gone past that, so our co-latitude is even greater. We've continued to walk due south towards the Earth's equator, and now we see that the horizon is off in this direction. I know that because I've drawn the ray tangent to the Earth at this point. So this is your body. This is the direction to the zenith. And if you have to look in this direction to see the sun, you're now finally looking above the horizon. So this is the altitude of the sun, and we can see from this picture the relation that we saw earlier. Okay, so I've written, remember earlier we came up with this relation. The sun right now is below the celestial equator, so delta, don't forget, delta is a negative number. Now, if we start with theta, theta is this angle here. That's the largest of the angles. In fact, theta is actually the sum of the absolute values of these two angles. But don't forget that since I haven't drawn the absolute value symbols here, I'm talking about a negative angle. So if you take this co-latitude, which, you know, if I had to guess, it looks like 40 degrees maybe, and then you add a negative number, you're actually making the number even smaller. So say this was 40, and the declination here was negative 10, for instance. 40 plus negative 10 would give you 30, but it's still a positive number, okay? So you're taking a number like 40 and adding a number like negative 10, you still end up with something positive. That's a positive altitude. That means that the sun is above the horizon. But this formula works regardless of whether delta is positive or negative. It doesn't matter if the thing that you're looking at is above the celestial equator at that time or below. Just make sure you include the appropriate sign, positive or negative. Okay, continue walking. Now the co-latitude is even greater. We're still adding a negative number. The sun's declination is still negative, but because theta is even bigger now, the altitude will come out even bigger. So this is the direction. If this is you standing here, you'd look in this direction to see your horizon. You would look in this direction to see the sun. The sun is above the horizon, and your altitude is now bigger than it was before. This is the equation that we'll be using in the spreadsheet. You just need to know your co-latitude, which is 90 minus your latitude, and you need to know the declination of the thing that you're talking about. Let's do that now in the spreadsheet. Here's the spreadsheet that we already took a look at, and I'm just going to pretend that my local latitude or current latitude is something like 34.5 degrees. Remember, let's go with decimal degrees. And when you look up your location on Google Maps using the method that I showed you, they should give you those numbers in decimal form. Longitude, I'm not going to worry about that now. You will have entered that already. Time zone, yep. Okay, now day one, as I recall, yes, something around October 29th. I think the time was maybe 11:38. And this column requires you to enter the declination of the sun. Now, how are you supposed to know that? That's not something you go out and measure. The altitude is what you measured with the clinometer at local solar noon. That's this time here, whatever time you found for your location. So the declination we will have to get from Stellarium. So let me go back into Stellarium on October 29th, close to my location around that time. Okay, I've put myself in October 29th at 11:38, and I'm making sure to check that the time zone is UTC minus 8. Let's just go with UTC minus 8 the whole time, which is not daylight saving time. And sure enough, the sun is on the meridian, so I was right about the time. I would like to know the sun's declination. Well, you can't tell just by looking in the sky. We don't have any way of measuring that directly. But if I click on the sun, they're telling me that the declination on today's date, see on date, is negative 13 degrees and 48 minutes. And let me once again change that back into decimal form. Oops, I believe that was actually the configuration window, tools, decimal degrees, please. Okay, negative 13.8. And I recommend now, as you finish this lab each day, when you go into Stellarium to confirm the time at which the sun will cross your meridian, at your latitude and longitude, it's got to be your longitude too, you might as well take note of the sun's declination at that time and put that in your spreadsheet. So negative 13.8 on this day at this time. Now, I'm going to speed up time here. Actually, let me just click through the days. I'm going to hit the plus sign to go ahead one day. Watch what happens with the declination. It's definitely decreasing. It's gone to negative 15 and then negative 16. It's going to continue decreasing until the winter solstice. Now, I misspoke in the previous video. I think I said December 1st. The solstice happens around December 21st or 22nd. That's when the sun is at its lowest point on the celestial sphere, around negative 23.5. So we're not there yet, but it's rapidly changing, and hopefully you're seeing it change from day to day. So let me go back into the spreadsheet. The sun's declination on that day was negative 13.8. I think I got the date right. You're obviously going to be more careful than I am here. Now, calculated altitude. This is where we use the formula from PowerPoint. I'm not going to go back to the slide. Hopefully you remember that the altitude is supposed to be the colatitude theta plus the declination delta. So I'm going to say equals. I typed the symbol equals. Colatitude, okay, well, colatitude is 90 degrees minus latitude. So I can say equals 90 minus this latitude, the latitude that you enter into that cell. Now, if you do this entire lab in one location, and I assume that you will, that's not going to change. Your latitude won't change. So I would like to always refer to that cell. And so I hit F4. F4, see the little dollar signs that popped up now? That's called an absolute cell reference, so that I'm always referring back to that cell for the latitude. So what I've really done here is actually enter theta. This formula, 90 minus latitude, that is the colatitude. And you don't want to enter a degree symbol there. That's going to confuse Excel. So just type it in the way I've done here. Okay, we're not done yet. Altitude is colatitude, which I've just typed, plus declination. And that includes the sign, SIGN, whether the declination is positive or negative. So it is important that you include the minus sign here. If we were in the summertime, that declination would be positive. So I click on the cell for declinations. See what I've done is actually click on the cell, and the address of that cell is column E, row 9. And now I hit enter. And so I've calculated that the altitude should be around 41.7. Based on the diagram, the geometry that I showed you, and the information given to us by Stellarium, which in other words, the declination. Based on that and your knowledge of your location, what's your latitude on Earth's surface, you expect the sun's altitude to be this many degrees, 41.7 at local solar noon. And sure enough, remember in the first slideshow, I went out on that date and used the clinometer app on my phone to measure the sun's altitude, and I found that it was somewhere between 41 and 42. So I think I chose to say 41 and a half because, excuse me, I didn't have that much precision with that thing. Okay, so that's pretty satisfying. And what you'll do is just repeat this all the way down during these 2 weeks. So remember, the time doesn't change by much. Local noon happens almost at the same time every day for those 2 weeks. Changes a little bit. The declination will change. It's changing every day because the sun's moving around the ecliptic. So you will have to update this number. But the formula does not need to be entered every day. What you can do is this little trick. It's a lot like, well, I think you saw this in the Revolution of Jupiter Moons lab. I hover over the lower right, I double click. And nothing happened yet because I don't have any data in these cells. But after you've filled out all these cells, this will automatically be calculated for you. That's why I needed this absolute cell reference, so that we always refer to the same box for latitude. Okay, what if I click and drag here? Yeah, it's giving me all 55s because it doesn't have any numbers here yet. But as you enter those numbers, all of this will update. And on a day where, yeah, so over here, remember, there will be days perhaps where you can't get out of work or whatever, and you can't enter the altitude. You can just leave that entire row blank. Maybe go back later and just delete that row. I'm okay with that. Now, for percent discrepancy, I'll demonstrate it right now. Well, discrepancy is a fancy word for difference. So what's the discrepancy between the expected altitude of the sun on that day at noon and what you actually observed with your clinometer? So I'll say equals, open parentheses, and let's go with your observed altitude minus what you expect from the diagram. So close parentheses, that's the difference between what you measured with your clinometer and what you would expect from Stellarium. And then let's compare that to what we expect. So it's not enough to just take the difference. We need the difference compared to the expected value. Lastly, to convert into a percentage, we multiply by 100. Okay, so it's difference in parentheses over expected, or in other words, the calculated altitude from Stellarium using the declination, and then multiply by 100. Now that's way too many digits. That's garbage. So let's use this button and just keep one decimal place. Okay, so I feel like I got lucky here. My measured altitude for the sun was off by 0.5%, 0.5%, which tells me that using the clinometer app and knowing ahead of time when to go outside, it works pretty well. So I find this satisfying. You should find that your percent discrepancies are similar on each of the days that you do a measurement, hopefully around 1%. If there's something like 20%, you definitely did something wrong. You don't need to fake these numbers because I'm going to check that everything's consistent. But you'll just repeat that for each of the days that you actually observe the altitude of the sun. Okay, the last thing to look at here is why the sun's declination is changing all the time. What's up with that? So here's this awesome simulation from the Nebraska Astronomy Applet Project website. And be advised, in 2020, I think it's December, Google Chrome will stop supporting Flash. That's a bummer. But the site has a workaround. They're still going to allow you to run these simulations in a separate app. But I've got this running in the browser. And of course, this picture is not to scale at all. The sun is way bigger than the Earth, and they're also much farther apart. But let me hit play here, and we see the Earth making its transit around the sun. Most of you guys have done this 19 or 20 times already. I don't mean you've watched the simulation 19 or 20 times. I mean you've been around the sun 19 or 20 times. And I'd like to look at this from the side, so I can click and drag. And they are indicating the direction of Earth's axis of rotation. So let me pause here. The plane of the orbit, that's, if you could like pass a sheet of paper through this circle, that piece of paper would represent the plane of the orbit. And when you look at it from the side, Earth's axis of rotation is not perpendicular to the plane. You might think that it would poke through like this, but it's tilted a little bit. That tilt is something like 23 degrees, and they're giving it to us right here. But as you watch the sun go around, so when it's over here, the sun's axis, did I say the sun go around? As you watch the Earth go around, the Earth's axis at this point in time is tilted towards the sun. By the time the Earth gets over here, its axis will be tilted away. And of course, that's the reason for the seasons. Maybe you've heard that we're actually slightly closer to the sun in February, in the middle of winter, or towards the end of winter. So our distance to the sun has virtually nothing to do with the seasons, because that distance doesn't change much anyway. It's all about the tilt of the Earth and the amount of time we spend in sunlight versus darkness. Okay, so notice the sun's rays, as they strike the Earth, they can be visualized over here. And what are we even talking about here? The whole point, yes, was to conceptualize why the sun's declination changes. So remember this, the equator on the celestial sphere is the projection of Earth's equator. So Earth's equator would be one of these blue lines here. Extend that outwards. So I'm kind of sweeping out with my mouse here. I'm sweeping out the direction to the celestial equator. Right now the sun is below the celestial equator. In other words, it has a negative declination. That's why the rays look like they're coming up from below here. But several months later, and that's going to happen right about December 21st here, when the sun is at its lowest point. See how the rays are really inclined? And now, as we approach January 1st, you see the rays are coming back towards parallel. We're getting through February, sometime late March. I'll pause it right around that time. Okay, it's kind of difficult to conceptualize from this diagram, but when you look over here, it's kind of clear that the sun is off in this direction. It's neither above the celestial equator nor below. It's practically right on top of the celestial equator with a declination of 0. After that, the declination goes positive again, and it continues to increase all the way until late June, when it gets to something like 23.5. So the reason that the sun's declination changes cyclically on a yearly basis is because the Earth is simultaneously orbiting the sun and it's tilted towards the sun. Well, I shouldn't say it's tilted towards the sun. The axis of rotation is tilted towards the ecliptic. Even that's kind of imprecise. I'll say this, the axis of rotation is not perpendicular to the plane of the ecliptic or the plane of the Earth's orbit. So sometimes, like in the summer, Earth's northern hemisphere is tilted towards the sun. 6 months later, 6 months later, the northern hemisphere is tilted away from the sun. And that's all we really need to know. So the daily change in the sun's altitude that you observe during this 2-week period is a result of our orbit around the sun and the tilt of the Earth's axis. You're directly observing the change in the sun's declination, but because of our latitude, we're having to turn declination into an altitude observed locally at noon. And I'll come back with a third video talking about the daily change in the time at which the star Fomalhaut culminates. That's a separate topic. And that video will be shorter than this one. Have fun with these observations.